Hi everyone, welcome back to our channel. I'm Shakur and today we are going to work on problem 4.3. This question falls under the category of bending stress in beams, and it's a classic types of problem you will see in mechanics of material. Let's read the question. Using an allowable stress of 155 megapascal, determine the largest bending moment M that can be applied to the wide flange beam shown. Neglect the effect of the fillets. Here we are going to write the basic formula of this part. We have sigma equal M multiplied by C divided by I. So to get the moment of inertia of this I-beam, we'll split it into three sections and simply add up the moment of inertia for each one. First part is this one. Second one is that part, 2, and that's the third part. According to the formula we have for moment of inertia, we know I it's equal for rectangle, it's equal 1 divided by 12 b multiplied by h to the power of 3 plus area multiplied d to the power of 2. Here for I1 we have 1 divided by 12 multiplied by, here B is equal 200 millimeter, 200 multiplied by H is equal 12 to the power of 3 plus A equal 12 multiplied by 200. 12 multiplied by 200, and the distance of the center is equal this part minus the center of this rectangle. It means we need this distance, which is equal 220 divided by 2, 110 minus this part, it's equal 6. 12 to the divided by 2, which is equal 6. 110 minus 6 is equal 104. And here we have 104 to the power of 2. Here we have 2, which is approximately equal 25.9872 multiplied by 10 to the power of 6 millimeter to the power of 4. Let's go to the next step. It's for I2, which I2 is equal 1 divided by 12 multiplied by B, which B here is 8, and multiplied by H here is equal this part. That's equal 220 minus 2 multiplied 12, which equal 196. 196 to the power of 3 plus 0, because the center of this rectangle, it's the center of the shape we have. And here I2 it's equal 5.0197 multiplied by 10 to the power of 6 millimeter to the power of 4. In the next step, for I3, it's exactly like I1, and it's also equal 1 divided by 12,200 multiplied 12 to the power of 3 plus area is equal 12,200 multiplied by, and also here we go, we have this distance, which here is the center, and again it's equal 220 divided by 2 minus 6, which is equal 104. 104 to the power of 2 is equal 25, 0.9872 multiplied by 10 to the power of 6 millimeter to the power of 4. And I total, it's equal I1 plus by I2 plus I3, which that's equal, here we have I2 and I3, and here we have I1, which equal 506.944 multiplied by 10 to the power 6 millimeter, which is equal 5956.944 multiplied 10 to the power of minus 6 meter to the power of 4. And for C, because the cross section is this symmetric, our centroid falls right here, which is equal, which is equal 1 divided by 2 multiplied 220, 110 millimeter, which is equal 0.11 meter. And for this formula we have here, we have C, I, and according to the question we have stress and we need a moment. And a new formula for moment, according to our first formula, we write moment is equal I multiplied by stress divided by C, which is equal total I, it's equal 6.944 multiplied 10 to the power of minus 6, and this stress is equal 155 multiplied 10 to the power of 6. Here we have megapascal, and now we have pascal here, divided by 0.11, which is equal 80.2 multiplied 10 to the power 3 Newton meter. That's it. Easy question.